So welcome everybody. I'm Janos Buttgereit. I'm a software developer at Sonible. We're an Austrian plugin company building cool plugins. And today I'm going to talk not about plugins, but more about a building block we use in our code base, which is Victor. This is a new project. It's a vector library, and we call it Victor internally. On Friday, a colleague came up with this could be versatile container templates reconceptualized, I think. Maybe this will be the name of it. But yes, this talk will be about C++20 concepts, as we are using a lot of concepts in this implementation. Then I'll give you a rough overview of what is Victor about. It makes use of expression templates a lot, so I'll cover this a bit. Then we have a look in depth in the code of Victor, have a look at some benchmarks, and yeah, see what's next with this project. So let's get started with concept. Who in the room has already worked with concepts? Not so many people. Who's here because they are interested in concepts? I assume that. So I think I'm going to start with concepts, and this is the definition from C++ reference, and yeah, I think all questions should be clear now. No? Actually, when I first read this, my first question was, what problem are we actually trying to solve with concepts? I couldn't really figure it out. I would say I figured it out in the meantime, but I have had to think back a few years ago when I started with the Juice framework. I had a situation when I had to deal with integer sample buffers, and I thought, well, just let's take a Juice audio buffer int for it, and I might have written a function that looks like this. So nothing fancy here, we just multiply the content of the buffer by a static factor of 2. And the question is, will this compile? Well, let's try it out. I have the very same demo code here. And if I hit compile, yeah, I compiled it before and it works. Great. Now you could say, well, the audio buffer is a much simpler way to apply some gain, which would be buffer apply gain of 2. And now if I try to compile it, this should work, shouldn't it? Oh, I get a compiler error, which says error no matching function call to float vector operations clear. I have no float vector here, it's an integer buffer. So what's the problem? I probably should have read the documentation, which says the Juice audio buffer is a multi-channel buffer for floating point audio samples. So using an integer audio buffer was the wrong thing in the first place. Now, templates, in this case, the template type can be anything. And concepts give us a new way to restrict it. So I'll just fix it for the Juice people. We can stick a requires std floating point type here. And if I recompile the example now, it will still fail to compile, but with a completely different message, which means error, constraints not certified for class template audio buffer with type int, because int does not satisfy floating point. And I think this is a lot clearer. We directly know, okay, we should have never put an int in here. And so this is basically what concepts are about. Constraining template arguments to only a certain subset of types. Okay, now I'm going to present you our Victor library, which is definitely capable of working with integers among other types, and I've brought you an example here. So you see Victor vector, Victor array, and Victor span. These are the three basic types of our library, which existed quite a while in our own code base, but we are currently refactoring it to the state I'm going to present today. Victor vector just wraps a std vector. Victor array wraps a std array, and Victor span wraps a std span. Nothing really fancy so far, but what's cool is that it adds a bunch of functionality to it. So if I hit compile here, first thing you see is that I'm going to increase the size here a bit, prints out the content of the vectors. Nothing really fancy. But now let's have a look at the span at first. Span is a view on data contained in another location. So now I can do stuff like c minus equals 10.0 and compile it. And now we see C changed, but also B changed, because C actually is a subview on the middle two elements of B. Nice. Now we can do something completely different. I'm going to comment out the span here. I can write out a C is A plus B. Let's run it. And we'll see. C now contains the addition of both containers. And notably, it figured out that both containers contain 4 elements. But I can do even more fancy stuff, like, let's say I want the square of both. So I can write Victor square, use the stream operator that you know from standard cout, and we'll get the square of it. And I can even go further and say well, I want the logarithm of the square of the sum of both elements, and we'll compute this. So, besides being a quite verbose syntax for mathematical operations on vectors, one thing that I want to show you in particular is what is the type of C. C is neither a vector nor an array, and I have a helper function here which just will print out the type name. And we'll see that the type of C is vector ln of Victor square of Victor add vectors of a Victor double and a Victor array double. So this is an expression template. Now, why expression templates? How to implement this function? A plus B equals C for a vector. Now, the most straightforward way could be this function, just an overload of the operator plus, taking 2 const references to 2 vectors, creating a temporary return vector of the same size, then adding both up element by element and returning this vector. And as you can think, this is nothing that you should do in real-time critical performance critical code, because it will allocate a new temporary vector every time you call this function. Solution to this are expression templates. So this is the same function as an expression template. Now we have a struct which wraps the addition. It takes 2 references to the sources, as before, stores them internally, supplies a size member function, which just returns the common size of both vectors, and overloads operator, the index operator, and it will return the sum of both vectors at a certain index. And then we can overload this operator plus function to just return an instance of this expression template. Now to make it work, we need another part. This is the vector implementation that we can assign this to. So this is a very basic implementation of this vector, not what our vector looks like. But I just inherited std vector for the sake of the example. I added this assignment operator, which takes the expression as a class template, then resizes the destination vector in case this is needed, and then loops over all elements and assigns it to this vector. Great. We get the sum, and now additional intermediate vectors were created since the expression is directly evaluated into the destination memory. Now, let's add another fancy function to our vector, which might be an assignment operator for any type of container that has a begin and an end member function. So we call a std vector assign internally, pass the iterators to it. And yeah, so this is another cool feature of our vector. Will this compile? Let's try that. I have the very same example here. And for the sake of an example, I took std list as the source container for this container assignment. They have a begin and an end operator. And I'm having this addition and will assign it here. And if I compile it, I'll get an error message telling us class member cannot be redeclared. Why that? Well, if we look at the implementation, we basically see two assignment operator functions which take one argument, which is a template. So to the compiler, both function signatures look completely the same, and it cannot distinguish which one to choose in which situation. Now, we know which one to choose in which situation because we know the exact requirements for the type, for the one and the other one, which are an expression, which should be evaluated with the expression overload, should be a type that has this index array subscript operator as a const member function and a size const member function. While this container for the second overload should be any type that has a begin and an end member function. And we can map these requirements directly to C++20 concepts. This can look like this. So I have 4 concepts here. This is the basic concept syntax. A concept always has a template argument or multiple template arguments. I come to this later. Then the concept keywords comes, a name for the concept, equals sign, and then any condition that has to be met. And then we can put this requires clause here, which just looks like a function. And basically, it behaves much like a function. We can pass arguments to it. Makes sense if we pass this template arguments that we want to constrain. But we can also pass additional arguments. So for the subscript operator, I need some index value. And then we have this function body. And all that this concept requires is that this function body would compile to some valid C++ code. This is not code that is executed at any time. It is just a constraint that in this function body we should have code that is valid C++. So if T wouldn't have this subscript operator or wouldn't work on a const reference, this would not compile and the concept would fail. In case this is the case, the concept will be true. And with this, we can constrain our 2 functions. So the expression overload has the requirement that it has a member function size and a subscript operator. So you can see we can combine templates by adding an and, an or any other conjunction. And the container overload has the begin and end member function. And this actually solves our problem. I'll show it later. But we can do better. We can wrap all these combinations into a single requirement. So we can combine concepts. We can write this is-expression concept, which is basically the logical and conjunction of the has subscript operator and has mem size function size. We can do it differently with, which I showed you with has iterators. So we can just put in multiple statements in this function bodies, which should all evaluate to something valid. With this, I can refactor it like this, which is quite decent from my point of view. But there's another syntax option which I really like, and this is we can replace this class or type name keyword in the template list with the actual concept. So now our code looks like this. And this is just super beautiful syntax from my point of view. And yeah, we can try this out. I have this one here. And now everything should compile. We see the output here. Yeah, because it only picks this overload if the expression conditions are met, and this overload if the container conditions are met. Now we could do something maybe not that clever, but what if I made this a std complex float instead? I still can assign a float to a std complex float. This should work. Will this also work? Because I only have real numbers in here. Maybe this will work. We could assume it. If I hit compile, we will quickly see that it does not work because the assignment down here in the assignment operator, the for loop, does not work because you cannot compile, assign a float, a complex float to a float. Still, this might be confusing for users of the library because they don't exactly spot the real error from looking at this output. So we might need to refine our concept. So we have a second condition, and this is that our array subscript operator returns the correct type. You see, I added this as a condition here. And now our template list contains two arguments: the actual types that we want to constrain and the expected return type. The size member function still has the single type, and now the combined is expression with return type concept forwards two template arguments to the subscript operator concept and the single to the size concept. Now you might think, what does the syntax look like if I replace the type name class keyword with this concept and it has two template arguments? Well, the C++ standard also covers this case because it will only take the first template argument to constrain the type, and all further template arguments from the second one on, if there are any, can be replaced by something custom. So now our constraints looks like this. Is expression with return type t. So t now is the element type of the vector. And t will actually replace the return type, the second template argument in this concept. And with this, I have it over here. We still don't get a code that compiles, but again, get a better compiler message, which is now candidate template ignored, constraints not satisfied with expression this and that. And we see because expression with a return type complex float assigned to float evaluated to false. So again, this is a case where the error got a lot clearer through constraint. Now I have a third example over here. We're not dealing with numbers here, but instead with a std string. Should this compile? Why not? Std string has a plus operator defined. So this addition will work, we see it. But it might be that you don't expect anyone to pass in a string in a vector mass library. This is just not going to make so much sense. And it can be that there is a case, like we have seen in the juice audio buffer example, that some underlying code just does not expect this to happen. So we can do one more thing, and this is to enable or disable this assignment function itself based on the template type of the vector. So in case we don't have an arithmetic type as the vector type, we just disable the assignment of a mass expression at all by sticking a require statement right after the function declaration. This is the second way to constrain something with concept. And there's one more thing that's special here. We see I'm using std is arithmetic v, which is basically a bool constant from the type traits library. It's not a concept. So we can see concepts and bool constants are somewhat you can change between them. So you can just assign a bool constant to a requires clause, and if the constant is false, this will evaluate to a not met concept constraint. So yeah, this will just disable this member function, and then we again get the error message that adding strings is nothing that we would expect. Great. So as I said, this is not the real code that we have in our code base. And our vector library looks slightly more complicated. And I want to just have a glimpse into it. And I won't go into the very deep details because it would just be way too much code for this talk. But I will start with how an expression template looks in the vector concept. So this is just the square expression, which you have seen in the introduction example. All our expressions have an extent, which is basically borrowed from std span. So this will be the compile time constant size if the source has a compile time constant size, such as in std array. Or it will be std dynamic extent to tell us, okay, the extent is known at runtime. And the second template argument is the source type of the expression. And then we have a constructor that takes some source arguments and forwards it to an internal member of source type. Now you might wonder, the examples that I showed looked a bit more like this. We don't see any call to this square class here. We don't instantiate a square instance here directly. We rather use this stream operators. What do we actually do here? And as you might know, the stream operator is only defined on instances. So you can't have a class with a static stream operator. This just doesn't work. So ln, vector square, vector sign, as you see here, are all const expression variable instances. And they have an overloaded stream operator for different purposes. So now if we look at all these examples, here, the compiler will evaluate this expression from left to the right. So we see that we feed such an instance of whatever this is, we'll come to this soon, with another instance of this. Here we feed the result of this overload of operator plus, which is basically an instance of the add vectors template. And here we directly pass in a vector array as a source to it. So behind the scenes, we have this expression chain builder class. So all our templates are defined like this, the implementation, and at the bottom of our header files, we have this expression chain builder, square, square. And the expression chain builder is basically this class. It's a bit tiny here, but it's not that important. It just has 5 overloads of the stream operator, all taking a single template argument, but all constrained to these different situations that I showed you. So if we feed in another instance of this chain builder, then it will just concatenate these chains and return a new one. If we put in the result of an overloaded plus operator, it will add the expression to the chain and return the new expression. And if we add any of our containers, it will just put a reference to this as a source type and return the equivalent expression. So this is how we make this syntax possible. And basically having concepts allows us to easily distinguish between all these different cases to test which type we actually feed into our expression chain, which we are building. Now, again, a slide with a lot of code. I'll zoom in a second. So this is what the square expression really looks like. It's much more than just this simple index operator and the size and the constructor. We rather have multiple ways to evaluate the expression. So all our expressions that we implemented have at least this index operator for the most basic way to evaluate the expression. We try to make them all const expressions, which is handy. I come to this later. And then it has multiple optional other member functions, which can evaluate the expression on a whole AVX, SSE, or neon register. And we can evaluate the expression using accelerated vector libraries such as Intel IPP or Apple Accelerate behind the scenes. So each expression is free to implement either of these or none of these. And we see that all of these overloads are again constrained by concepts. So for the AVX overload, we actually require that we are on an x64 architecture or for the Neon on an ARM. Otherwise, this will be disabled entirely. Yeah, and on the other hand, we have the assignment, which is again a quite complex function. I'll zoom into the most interesting part. So this is in the container itself, the base class for all our containers, vector array, vector span, and vector. It has the signature assign expression template. You see the expression template is again constrained to take an expression. And then we just check, okay, is this function constant evaluated? In this case, we swap the whole code block and just jump over to the basic for loop. And as I said, all the basic index operator versions are const expression as well. So in case we are in a const expression context, we can evaluate this whole expression chain as a const expression, which is great. If we are not, we are trying to pick the best suitable option to evaluate with whatever our platform and our expression combination has available for us. So I have written these concepts like has blah, 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 where blah, blah, blah is a member function. And so we check if this expression has this evil next vector op in expression chain function. By the way, this was probably the name discussed the most during code review for this class. We just didn't find any better, shorter function name to write what's happening inside this. But this basically calls an IPP on accelerate function, takes the destination pointer where to write the destination to, and returns the source for the next chained operation. So we see we put in the data pointer of the destination container to this function call, and if it's available, we just evaluate the whole expression chain using this crazy good mass libraries. And if it's not available, we'll go to our hand-rolled SIMD loops as a next fallback strategy, starting with AVX if available, with SSE. And if all does not fit, because we only define it for, let's say, float, and we are working on integers, we will fall back to the for loop. Yeah, this is basically how it works. And another interesting thing to mention here is that you see I put this has eval next vector op an expression chain concept into an if const expression statement. So as you might know, if const expression expect us to pass in a bool constant again. So we cannot only take bool constants and apply them as requirements for concepts, but we can also convert concepts back to bool constants in a constant evaluated context, which is quite handy and makes a lot of code quite nice. Okay. One last thing. We have some expressions that are actually compositions of multiple individual expressions. I brought you our magnitude to dB expression here, which will compute the log 10 of the source, then multiply this by a decibel constant, either 10 or 20, depending on the context. And then we'll clamp the result by a minimum dB level. Basic evaluation of a decibel computation. But yeah, we see I just nested these expressions manually here instead of building up the expression chain with the syntax that I showed before. And I can put this whole nested expression thingy into this expression chain builder again and export it as an easy-to-use Mac2DB expression. Okay, a lot of template stuff. You could ask, is it fast? And I did ask this myself too, because at some point you don't really know which choices the compiler will make anymore if templates grow that much. And I thought the easiest way to find it out is to look at the assembly code. And what I did is I installed a compiler explorer locally on my machine here, so it has access to my library. And I just compiled this basic example, which has a source array, and it assigns the result of this Mac2DB expression, which is actually 3 nested expressions, to another array, and then returns the last element of it, just to make sure that the compiler does not throw away our result. And you don't have to be an assembly expert to spot the obvious parts of it. We see these 3 lines: call vv log 10f, call vdspv as mal, call vdspv as threshold. So the compiler really managed to see what's going on here and put in calls to these 3 Apple Accelerate library functions in here. And in between these calls, there are just some very, very cheap operations. And this is basically the same assembly that would have been generated if we wrote this DB calculation by hand using Apple Accelerate calls. The same works for Intel IPP, by the way. So this is really great. I was really amazed by this output when I first tried it after implementing this for quite a few weeks, when I was at the point to finally test this out. But I have an even cooler example for you. So now we have this don't use acceleration filter, which does nothing fancy, but just removing all those functions which are available to the compiler for accelerated operations, which are preferred in our assignment, as you have seen before. So now the only choice the compiler has is to take the basic for loop. And now if we go down to the main function, we see it's ridiculously small. It just returns 9. Because 9 is the equivalent of computing the decimal value of 3 and casting it to an integer. So you see the compiler managed to put all this template stuff, treat it as a const expression, figure out the end result, and just return 9. I was really amazed when trying this out for the first time. So yeah, I'm working with the last Apple Clang 14 chip with Xcode 14 here, by the way. So I think they really did a good job. We also did some benchmarks. So again, this Mac2DB expression, I tried to write it 4 times. The first is the simple expression as I showed you. The second one is the don't use acceleration version that I showed you, but this time not with compile time constant values, but with random values, so that it's really executed as a for loop. Then the manual for loop, and then the direct accelerate calls down here, which is probably the worst of all 4 versions from a readability point of view. And you might ask, where is this orange line exactly hidden behind the red line? So also the benchmark shows us that this code compiles down to the real equivalent of writing out these clunky C-style function calls by ourselves. And we also see that the unaccelerated version and the manual for loop are basically the same. And they are basically quite a bit slower. So using these accelerated functions really makes sense and really makes our code execute faster, which is a cool thing. Still, not everything is as bright shiny as this one. I benchmarked a simple multiplication. And here results are a lot closer. So you see that even the hand-rolled AVX loop is the slowest one. So this showed us, okay, we cannot always expect the compiler to magically do the best thing possible, or we cannot expect us to write SIMD code that is magically just faster as some Intel IPP or Apple routine. Question over here.
Do you look at the assembly of this? Because I wouldn't be surprised if the compiler has vectorized it for you, even the...
Yeah, if it's a simple multiplication, I wouldn't be surprised if the compiler has vectorized it for you, which would explain why everything is so close.
Yeah, I would expect this too. Probably the compiler will have inline vectorized this multiplication. And this is just to prove the point that the compiler is already quite good at making simple code fast, and we don't always need to write the super fancy SIMD whatever code in order to get fast code. So this is basically to just prove this point. Don't always assume that such fancy stuff results in fancy fast computation results. But yeah, to come to a conclusion, this is basically what we will be working on next. So you have seen the assignment where we just assume that this accelerated function call will be the probably fastest option, followed by an AVX, followed by this and that, and the follow might be the less fastest one. And for us, next steps will be to really benchmark a lot of combinations and try to figure out if we can do better in making a prediction which code path might be the fastest one for a given combination of chained expression templates. So this is actually a problem we are currently working on. And yes, I'll come to a summary now. This was a small glimpse at the project. Throughout the project, I really learned to love concepts. Concepts just take writing highly templated C++ code to a new level. I could have shown our old implementation, which we are working using in our shipping products at the current time. We will be replacing it soon with our new implementation. This uses some SVNI things, and this is just the most ugly code I have been forced to write in order to implement something equal with previous C++ standards. And we also saw that modern compilers are crazy good at fully inlining giant template structures. Now to the project. Victor has gone public today, so you can access it on our GitHub account. But Victor is not feature complete yet. We have implemented a basic set of functions so far. As I said, we have the previous version in our internal code base used very heavily. So this is how we write vector-based DSP code and other code. And we are planning to swap it out once we have reached an interface that has all the features that our old implementation that has grown over years supplies. So we have a GitHub issue backlog full of functions to implement still. But it seems to work, and if any one of you wants to contribute to this project, we would highly appreciate it. And as I said, we still need to do some fine-tuning to really be sure that this is a very efficient and fast vector library. All right, now it's time to ask questions if there are any. And if you're interested, just go to our GitHub account and have a look at the repository.